All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, let me start over. Geometry and metrics. All right, so we began by defining, a geometry, right? So we said G, if it goes from V cross V to the reals, where V is a real vector space. And here I'm thinking finite dimensional. I mean, I'm not saying that there don't exist infinite dimensional examples. I just don't know them off the top of my head. So we have a finite dimensional vector, real vector space. We have G, a mapping from V cross V to R. Then G is a metric, right? If G is bilinear, symmetric, and non-degenerate. All right? And we've actually talked about symmetric and bilinear in previous lectures, so I won't belabor those, but the non-degeneracy gave me a little bit of trouble last time, so let's kind of focus our attention there. Trying out these new markers, see what happens. So non-degenerate means for us that G of, I don't know, I think the other ones are kind of better. G of x comma y equals to 0 for all x in the vector space implies y is equal to 0. If you want a replay of what went wrong last time, I was completely ignoring this part. I was just working over here, somehow trying to get to what I wanted, which is crazy. The implication, this implies that, is what gives you the non-degeneracy, which is what tripped me up last time. Anyway, that's non-degenerate. Notice that an inner product, what's the difference? So if we're talking about an inner product from on a real vector space, right? So this is also bilinear. And it's also symmetric in the real context. But then we have the condition that xx is positive for all x not equal to 0, right? That was the axiom for the inner product, right? And so you notice that if we have x comma y is equal to 0 for all y in the vector space, right? What's that tell us? That means that, well, for example, x comma x is equal to 0, right? I'm sorry, that's not what I want to say. I want to say y comma y is equal to 0, right? Sorry, the roles of x and y are a little bit different here, aren't they? So I can take the particular case. Oh, what have I done? That was supposed to be an x. Come on, idiot. Golly. All right, so for this equal to 0 for all x and v. Well, in particular, that means that the inner product of y and y. I'm messing this up. Let me start. Let me just write down what I wrote when I was thinking more clearly earlier today. All right, so recall, we proved for inner product space that the inner product of x and x is equal to 0 if and only if what? If and only if x equals to 0, right? That was something we derived for inner products. Thus, if we have the inner product of x and y is equal to 0 for all x and v, that implies that the inner product of y and y is 0, which then, by our work in inner product spaces, implies what? Y is 0. What does that mean? That means that if we assume this right here, right, we get that, which proves that any inner product space has a non-degenerate symmetric bilinear form, if we're talking about real inner product space. In other words, every inner product is a metric. Okay, that's the proof. Now, I did an example last time which was 4-dimensional. Let me kind of rehash that as a 2-dimensional example. That'll make it easier for you guys to follow. So the immediate question that you should ask as math majors is, all right, well, we already know inner product spaces. You're introducing this concept of a metric. How is it different? I mean, you just shown me every inner product is a metric, but is every metric an inner product, you know? And so a nice example is given by R2 being your vector space, and we can say G of x comma y is equal to minus like x1 y1 plus x2 y2. I guess we've been using upper indices lately, but whatever, it doesn't matter. Up, down, whatever, okay? I'll leave them down for this example. See, this, of course, we could write this as x transpose times the matrix minus 1, 0, 0, 1 times y, right? Like, that's a formula that we could express G with. And so this is the matrix of G, right? And I'll soon call that, let's call it, you know, we can use this notation here, like this is big G. It's the, you know, the matrix of the bilinear form with respect to the standard basis. And you can see that that matrix is symmetric, right? And so if the matrix of the bilinear form is symmetric, the bilinear form, I mean, you could prove symmetry here easily, right? And you can also prove linearity. Like, linearity is pretty much immediately obvious from this formula, right? Because this is linear in x and this is linear in y, so we can prove linearity in x and y, which means it's bilinear, right? Like, that's a theorem. If you can write the formula as a vector transpose times a matrix times another vector, that's a bilinear map. Yeah. But I suppose the why is this not an inner product this warrants a little bit more investigation. And I think this is the thing I didn't do last time, which is why I'm revisiting this example, is we should just like try x and x, right? What happens if we put in a vector in itself? What do you get? Minus x1 squared plus x2 squared, right? And you see, there's really no reason that the difference of those squares should necessarily be positive, right? In fact, if you think about it, this is greater than or equal to 0 when? Only for what? For, you know, x2, well, let's say greater than 0, for x2 greater than x1, right? So like if you were to graph the situation, right? There's like it's not that it's not an inner product by a little bit, it's not an inner product by like half of all space, right? Okay? So like x2 greater than x1, that's up here. Or down here, I think. Yeah. Well, excuse me, I mean, that's true, but what's more generally true? right? So like both the lines themselves, right? And everything over here, we have the inner product. Listen to me, inner product. We have the metric here, g of xx less than or equal to 0. In particular, if we're on those lines, right? If we have x2 is equal to like plus or minus x1, that makes the metric here 0. So if g of like, g of xx would be equal to, plus or minus x1 squared minus x2 good grief. I can't do math. Minus x1 squared plus, golly, plus or minus x1 squared, which of course is equal to 0, right? It's like both of these lines through the origin with slope 1 and slope minus 1 are full of points where the inner product of any of those vectors with itself is 0. These are the so-called null vectors. If you think about this as space-time, they're light rays. And this is actually like the forward light cone, the backward light cone. People talk about this. These are like time-like vectors in here and there. And these would be like space-like vectors. If you think about x2 being time and x1 being space. Oh, dang it. Well, yeah. Anyway, well, let me shut up. Who cares? I don't have to teach you guys special relativity, right? My point is that this kind of, this metric actually comes up in special relativity as it happens, all right? Now, I have not proved the non-degeneracy, right? We could prove non-degeneracy for this, but I think I'm going to go on. All right, I have, in the notes I'll post on this, I have a simple proof of non-degeneracy for this example, but I should move on. All right, so next up, I want to define the matrix with respect to a basis. So, definition, given G, a metric from, say, a vector space. Ooh, that's bad. I've got G goes from V to V, which is just pure unadulterated nonsense. The metric goes from V cross V to the reals here in our context, okay? A metric. If we have basis beta equal to V1, V2, Vn, all right? A basis for V, all right? Then G equal to like G of Vi, Vj, right? Which of course we also could just call that G lower ij like that. So like the components of G, Gij with respect to the basis, that's the matrix of G with respect to the basis beta. All right, and as we'll soon justify, G inverse exists, and we will denote it by G upper ij, where in particular we have this formula. The sum j equals 1 to n of G lower ij contracted against G upper jk is equal to Kronecker delta I k. In other words, they're inverses. So, like, comment here, remark, right? For example 1, notice, G is equal to minus 1, 0, 0, 1, whereas if we think about Rn with, let's say, g of x comma y equal to x dot y, which by the way is x transpose times I times y, has the matrix of G equal to the identity matrix. And as I told you guys last time, Rn paired with the dot product is a geometry which we call the Euclidean geometry. Right? And the matrix there with respect to the standard basis is just the identity matrix. It's like the simplest possible case. Okay. All right, so theorem. Oh, first a lemma. Let me do the lemma first. Lemma. All right, given x and y in the vector space V and beta the basis as we were just talking about, for which x beta is, let's say, x upper 1, x upper 2, x upper n, and the coordinates of y upper with respect to beta are y upper 1, y upper 2, y upper n. Right? What am I saying there? I just mean x is what? Sum of xi vi, right? And y is the sum of over j of y upper j v lower j, right? That was our definition of coordinates and bases, and that's our notation, right? Standard notation. Then what? Well, then, oops, sorry. We can write g xy equal to simply x sub beta transpose times big G times y sub beta, provided we define Gij as we just did in the previous definition as all right. So which side do you think we should start on here? I think I'm going to start on the right-hand side this time. So the proof is just a calculation, all right? So if we look at x beta transpose times g times y sub beta, right? In terms of like math 221, that's the sum, I and j equals 1 to n, of x upper I, g lower ij, y upper j. Because it's a row matrix column product, and that's, in our current notation, what we have. And so this we can rewrite as, g of the sum of xi vi. Oh, fine, I'll do 2 steps here. I'm sorry, I'm skipping too many steps here. Sum I j equals 1 to n of, let's say, xi yj times g of vi vj, right? But then I can use the bilinearity of g to pull those summations and constants inside the little g. See, that's really g of the sum over I of xi vi, comma, the sum over j of yj vj. See, this is just by the bilinearity. And that's just g of x comma y, right? So there you go. We've got the lemma. This is how we calculate given a basis and components in the matrix, right? This is how we do it. All right, so the theorem I was about to state is what I got hung up on last time. So hopefully I won't get stuck today. The theorem is that if we have the matrix of a metric, that matrix must be symmetric, symmetric and non-degenerate. In other words, invertible. Let's see here. So theorem, if Gij is equal to G of Vi Vj for basis beta equal to V1 Vn, where G is a metric for V, which is of course the span of beta, then G transpose is equal to G, and G inverse exists. Right? Now I was trying to prove this in a more focused context. Last time I was trying to prove it just for like a standard matrix of a bilinear form in Rn, but we might as well just do the full proof, the same trouble. All right. So here we go. Let us suppose that G times the coordinate vector of y sub beta is equal to 0. Right? Before I go any further, what do I want to show? And why would showing that, forget about the symmetry for a second here, we'll come back to that, that's easy. Right? I mean, we could maybe just dispose of that first. Why is it symmetric? Symmetry of the matrix follows immediately from symmetry of the metric, right? Like, I don't want to clutter my other proof, but Gij is G of Vi Vj, right? But by symmetry, that's G of Vj Vi, which is equal to Gji, right? Therefore, it's symmetric. G transpose is equal to G. But the harder thing is proving G inverse exists. What are equivalent conditions to the invertibility of matrix we learned in Math 221? You should be able to name about 10 of these. First, we're talking about an n by n matrix. What are the 10 equivalent characterizations of its invertibility? First of all, of course, there exists a matrix that when you multiply on the given matrix, on the left or the right, you get the identity matrix. We proved in Math 221 that either the left or right inverse implies the existence of the other happening. Either one separately gives the other. That's one. Rank of the matrix is n, right? If its column space is Rn, that's another way. If the row space is dimension n, that's another way. If the determinant of the matrix is non-zero, that's another one. The determinant of the transpose of the matrix is non-zero, that's another one. But then the thing I'm actually thinking about, the null space is 0, right? The only solution to the homogeneous equation being 0 is perhaps one of the more important characterizations of invertibility. A matrix is invertible if and only if the homogeneous equation, right, has only the 0 solution, right? We spend a good chunk of our life in Math 221 looking at the case when that's not the case, right? For the eigenvector problem, we're looking at a matrix which is by construction singular, so it has non-zero solutions to the homogeneous problem, right? This is such a big chunk of Math 221. So my goal to show G is invertible is simply to show that this column vector must be the 0 vector. If I've done that, I've done my job. We have G inverse. Make sense? All right, so look, this implies that EI transpose times G times the y vector is equal to 0, right? For all I. I hope you can agree with that. Which also would imply that the sum I equals 1 to n of x upper I e lower I transpose of G times y sub beta is equal to 0 for all, like, you know, x1 through xn. In other words, if I have 0 n-fold times, I can multiply each one of those equations by x up or whatever, right? And then just sum those together. It's 0 plus 0 plus 0 plus 0. I still have 0, right? Great. But this implies that, you know, I have, I mean, that's the matrix of x with respect to beta times G transposed times y beta for all x in the vector space, right? Because the above holds for arbitrary coefficients. Yeah? And so it should be somewhat clear that I can make x upper, you know, 1 through x upper n to be whatever I need them to be by choosing the appropriate vector in the vector space. I mean, this, I think this is clear. But then I use the lemma, right? The lemma says that this is g of x comma y is equal to 0 for all x in the vector space. At which point I've met the precondition of non-degeneracy. And what do I get from that? Because G is a metric, this implies y is equal to 0. Non-degeneracy, right? Metric. Which then, of course, implies that the coordinate vector of y with respect to the beta basis is equal to 0, which implies that the null space of the matrix G is equal to 0, which implies that G inverse exists. There you have it. All right. With that, we can go on and define the musical morphisms. All right? So, like, let's see here. All right, here we go. So, let me just define them. Musical morphisms. If alpha is in the dual to V, then the sharp of alpha is a vector defined implicitly by, this marker's trash. Back to your home. Alpha of x is equal to G of x comma sharp alpha for all x in V. Likewise, Beta, I mean flat. Flat is a mapping from V to V dual is defined by flat of x acting on y is equal to g of x comma y for all x and y in V. Somewhere in this bag I've got a working marker. I'm going to find it. All right, so these definitions are nice definitions in that they do not use coordinates. Do you see that there's no use of the basis in these formulas? These are coordinate-free definitions of the morphisms. That's what is new about having a geometry. We couldn't do this for an arbitrary regular vector space. Like just a plain old vector space and its dual, there's no like isomorphism between the vector space and its dual space that doesn't require descending to the level of like picking coordinates and doing something with the specific choice of basis. But here, there's no basis, right? That said, it's nice to find formulas with respect to a basis, right? So let's do that. So suppose we're, number one, we're given x is equal to the sum of xi vi, all right? Then we want to think about flat of x. It's equal to the sum over j of flat of x acting on vj times v upper j, right? This is what I'm doing. I'm referring back to a discussion we had before. Any dual vector, right, can be written as the sum of, that dual vector acting on the basis times the dual basis, right? Here, v upper j acting on v lower I was Kronecker delta ij, right? Remember we talked about the dual basis before. I'm using that again. But, okay, what is this though? What is beta x? I mean, by definition, right above, right? It's g of what? X, comma what? Vj, right? V upper j. But we can also, of course, rewrite x in terms of its expansion. So we've got, and I'm going to pull that out, so we can rewrite this as the sum over I and j of x upper I, g of vi vj times vj, right? Which in our notation is the sum over j of the sum over I of x upper I, g lower ij, all times v upper j. And for that reason, physicists and adjacent mathematicians make a definition here that x lower I is equal to the sum I equals 1 to n of like x upper I times g lower ij. This is known as lowering the index. Of x. Well, you could say just x. I mean, fine, x of I. And that's the reason for this horrible pun. This is why it's called the flat map. We're like lowering the note. See it? Yeah. hilarious, right? Yeah, okay. But there's a stone cold formula for it, right? Like that's what this is how we actually take the flat of the vector. We contract against the metric like this. And number 2, right? We want to do the same, but for the for an arbitrary dual vector, right? How's that going to go? So number 2, if we have alpha is the sum I equals 1 to n of alpha sub I v upper I, because we can, remember, write any dual vector in terms of the dual basis, which we proved was a basis. You remember that? We did that. All right, so then what happens, we want to understand, sharp alpha, right? That is supposed to be equal to the sum j equals 1 to n of v upper j acting on sharp alpha, right? Times v lower j, because this was a general result we had, right? If x is equal to the sum j equals 1 to n of x upper j v lower j, then x upper j we could understand is really just vj acting on x. That was a general result we had. My brother said something interesting to me over Thanksgiving break. He said that, what is dual space? Well, every non-zero vector in dual space is a potential component function to a coordinate map. So really, what is dual space? It's the set of all possible coordinate maps, and 0. I thought, that's an interesting perspective. I think it might help students. I don't know. Does that make you guys feel better about the dual space? I've connected one thing you don't know to something else you don't know. Does that make it better? I don't know. Right. You guys know coordinates. What am I talking about? Don't take that. Don't take that from me. Reject my. Okay, so we want to find the formula for this basically, and so how do we define the sharp, right? Well, let's see here. So I have g of oh, my bad. My notes are playing tricks on me. So we have alpha of x is equal to what? It's equal to g of x comma sharp alpha, right? I mean, this is true for all x, right? But I think to make the most of this equation, we probably should put which x in? I mean, if we put in, we know that alpha I is what? That's alpha of vi, right? So if I put in, I have alpha of I is equal to alpha of vi, but that's also equal to g of vi with hashtag alpha. I'm sorry, no hashtags. No hashtags in my classes. It's a long-standing rule. I had to impose about 2015, as it turns out. First time I ever heard a hashtag was in a student presentation at the end of the semester. They were hashtagging throughout their presentation on the generalized Stokes theorem proof. Her name was Jeanette Luna. A very funny student. Anyway, where was I? All right. So this is equal to g of vi with the sum j equals 1 to n of v upper j of hashtag, I'm sorry, sharp of alpha v lower j, right? Which we can pull the sum over j out, and the thing we're trying to calculate out, which is v upper j of sharp alpha. Notice that what we have left then is g of vj, which is just g ij. Right? So I'll draw your attention to this equation, right? I'm trying to solve this equation for this. Right? So this is where the inverse metric has to come in. See, so if I do the sum over k equals 1 to n, sum over j equals 1 to n, thing I'm trying to solve for, right? And then I've got g I j, g I, oh, blarg. I meant to make that an I, sorry. GIK equals to no, I can't do that. Oh. All right. We will pick this up again on the projector. You gotta know when you're beat, you know. I always get into trouble on that board. That board is cursed or something, you know. I don't know. Do you guys believe in cursing? My brother used to have a theory that there was a particular room in Harrelson Hall, which is where we used to teach math at NC State, and that at some point a room full of particularly stupid college algebra students were massacred. And it left a stain on that room. Because anytime people took tests in that room, there was vast stupidity. So he had a whole theory of the room being cursed. But I think it was just because mostly people taught college algebra in that room. And, you know, or like business calculus or things like that. Things where the people are there not by their own choice, you know, but because they're forced to be there. So, anyway. Come on. Well, all right. I will post this, of course. It's probably like the next thing I need to type up in my notes for this course. All right, come on, there we go. So this is the stuff we did. Skipping past the proof of non-degeneracy. All right, so we made it to here. Ah, yowzers! Oh, be careful, I'm gonna get stuck down there. All right. So the point is, we got to use the inverse metric to solve for the sharp components. So what I do is I just take the equation that we have and multiply it by the inverse matrix and sum over I like this. And here k is free. And so when I do that, this gives us a Kronecker delta, which then kills one of the sums, leaves me with the sum over I, but not the sum over. See, that's still wrong. Stank. Well, apparently I made the same mistake in my notes, and I still haven't. I'll have to fix this. I'm sorry, guys, but this is true nonetheless. This is how the formula we will find once I do things correctly. I just need to clean things up. But yeah, when you raise the index, you just have to contract against the inverse metric. This is how that works out. Now, What's more interesting, and perhaps more germane to this course, is the fact that these are isomorphisms, right? And so my claim is that flat is in fact a linear transformation from V to V dual that is in fact invertible, and not just that, the sharp is the inverse map. So here's the proof of that it's a linear transformation. There's a couple different things to deal with. The one is that the map is into, right? Into means that the codomain is well stated. Is it clear that beta of x is in fact a linear transformation on V, right? I mean, I think it is, but here's the proof that it is. It's because we defined this to mean that, and then we have linearity in the second slot of V, because G is bilinear, so hence beta of x for any x is a dual vector, yay. But then we also need linearity of the map flat. The flat map's linearity is this kind of linearity, right? How do we understand that? Remember that the flat of anything is itself a dual vector. So to understand how a dual vector is, we have to let it act on something because it's a mapping. So I let it act on an arbitrary vector y. But then by definition, this is that. And now we're going to exploit linearity in the first slot of G to get the linearity of the flat map. Yay. So it's a linear transformation. And it's a, right. So I said I'll leave the show it's a, to show it's an isomorphism. The homework, that may be an empty threat. Maybe it's a threat I'll make good on like next time I post these notes. I don't know. But look, so like it's essentially this is like if you take alpha and you raise the index, we do it like this, right? But then suppose you take that raised index and you lower it back again, like that, right? Well, then you end up with a pair of metrics which are contracted, which gives you back a Kronecker delta, which brings you right back where you started. And so this is sort of illustrating the fact that they're inverses through the lens of the component formulas. But that's not the kind of proof of inverse we'd like to see in here. Oh, here, don't tell the future students. Here's actually the proof of inverse directly. This top proof is kind of tricky, actually. So I'm trying to show that the composition of sharp and flat is the identity. So in this direction, well, I'll let you look at that. But the proof in the other direction is actually stupidly simple. Like down here, if we have flat of sharp acting on x, by definition, that is G of sharp alpha with x. But then by definition of the sharp map, that is, well, this is by symmetry. But then by definition of the sharp map, this is alpha of x. But that holds for arbitrary x. Therefore, this is the identity. And that proves that it's an inverse. And that's actually enough. You don't really have to have the other one to prove invertibility, truth be told. Now, there's also, you can do things, you might call it tensor music, I don't know. You can use these things together to get from one kind of, one kind of multilinear map to another. Like, if T and S are like multilinear, T on V to V and S on V dual to V dual, right? I can make S from T if I use the sharp maps. See, I can take these dual vector inputs and turn them into vector inputs. And those I can feed to T. Or vice versa, I can take vector inputs and I can convert them into dual vector inputs and I can feed that to S. See, so I can go between, actually, and you can do this with mixed things too, right? Like I could, if I had, R's from V cross V dual to the reals, so I could, feed this R alpha, I could understand that as T of, well, leave the X alone, but sharp the alpha, So what this all means is in the context of a metric geometry, there's a natural isomorphism between multilinear maps that have the same number of inputs. If I have 3 inputs, right, and 3 of them are vector spaces, and then I have another one where 3 inputs are dual spaces, there's a natural isomorphism between those kinds of objects. And in physics, especially the physics of general relativity, these isomorphisms are used. Now, this is just a kind of fun calculation. I worked out that if you look at the flat mapping on the basis, it doesn't go to the dual basis. It actually goes to this. And if you look at the sharp mapping on the dual basis, it actually doesn't go to the basis. It goes to like this contraction of the inverse which is very satisfying if you just think about the general mechanics of index lowering and raising. It's consistent with the rule. Like we're raising and lowering the index of the basis and the dual basis in the same way we raised and lowered the indices of the components of said objects, which is kind of cool. And then finally, this is my last theorem to share with you guys this semester, assuming I don't find a way to put a new theorem on the final, but I don't usually do that, so let's not do that. This is known as Sylvester's theorem, and I think sometimes it's called the law of inertia, but I'm not exactly sure why. And this is probably a specialization of his theorem, truth be told, but if we have a metric, right, let's think about how we can put all the pieces together. We have a matrix of the metric. It's a symmetric invertible matrix, right? So the real spectral theorem says that there exists an orthonormal eigenbasis for it, right? And also, 0 is not an eigenvalue, because invertibility means 0 is not an eigenvalue, right? So that means that you can take the eigenvalues and you can put them in order, all the negative ones first and all the positive ones second, like I did here. I called them lambdas and I called them mu's. So I've got, G on E, G times EI is that, G times E bar is that, like that, all right? Eigenvectors, eigenvalues. I'm not saying EI and EI bar are the standard basis here, obviously, right? Well, if that's the case, then you can rewrite any negative quantity as minus the square root of its negation squared. Kind of silly, but you can do it. And of course, any positive quantity can be written as a square root squared, right? So if I look at these expressions, if I just basically, so the idea here is if I take the basis and I divide by the square root of the eigenvalue or the square root of the absolute value of the eigenvalue, something really cool happens. See, because this times that, we get a lambda over lambda, which is just minus 1, or down here we get 1. So if we use that, right, as our basis, gamma, basically take your eigenbasis and rescale it by the appropriate square roots, then all of a sudden you've got a basis where the metric is diagonalized. But not just diagonalized. I mean, we know we could diagonalize it. It's symmetric. It's diagonal with either minus 1s or 1s on the diagonal. And I think you can prove that the number of minuses and the number of pluses is, you're stuck with those. Like you can't, those are characteristic of the metric. So the Minkowski metric I showed you guys last time had r equals to 1 and s equals to 3. The one I did in example 1 today had r equal to 1 and s equal to 1. But the neat thing is you can always change your basis so it looks like that. In other words, in the abstract, a metric looks like a slightly tweaked dot product. So anyway, I will shut up. That's all I got for you guys. I'm supposed to give you a quiz Friday, right?